Hi, everybody. During Leon's presentation last week, he showed this interesting graph with a data set with different slopes and intercepts for the models to illustrate the effect of a multi-level model where you can have models within a model. And I found this example at this link that I thought I would adapt and share with you. So I've done that. The author does put code into R, but I did change a little bit here to fit more with how we do things in the class. The author is using the LME4 library for the mixed models, linear mixed models. And then we go ahead and we set up some independent response variables. There's an independent variable from a uniform distribution going from 10 to 40, 25 to 50. So each one of the independent variables is a little different. And then our response is calculated from our independent variable with a unique slope and intercept for each group, and then some random noise thrown in as well. So we can go ahead and run that. And then we combine those together into an independent set of data, response data, and then create a field data set for that as a data frame. So we've got our independent variable, our response variable, and our IDs, which are A, B, C, D, E, breaking up the data into 5 groups. Okay, and we can plot that, and looks like we've got a fairly linear looking data set, maybe, maybe not. If we do a linear model against that, we're doing pretty well, adjusted our square root of 0.86, little tiny p-value, so we could feel pretty confident about this, but maybe there's more going on. And before I do a plot of this, I want to show you something about how to get to the coefficients within a linear model. So if we print the linear model, you will see that there's a call and then there's coefficients. And we might want to get to these variables, the intercept and the coefficient, and we can do that by just going $coefficients. And that will pull out the coefficients. There they are in an array. And then we get each of the individual coefficients by doing that. And then we can go ahead and plot our data again and put our line through it. So there's our model. So yeah, there's something else going on, right? This is not uniform residuals. So we definitely would probably want to go further. And you might try to put a gamma against it or something, but let's try a mixed model. So here's our mixed model where we've taken our response variable against our independent, but we've added this extra term where we're also including the independent variable given these groups. And so we run that. Now here I got an error that it failed to converge, and I looked on the web. Apparently that's not a serious error, but I'm a little concerned about it, so I'm going to go ahead and run this again. What I found was that because of the random component, sometimes that linear mixed model is going to fail. There's 2 different errors I found, and I wanted to make sure I get one that didn't have any errors in it for you. So then I do a summary. And I should say it's based on the nature of the data as to whether or not it's able to converge to a good linear mixed model. If you get that error with your data set, please read on the web. There's blogs about how to interpret those errors. Okay, so now if we look in here, we can see that we've got our random effects and our fixed effects. Okay, and what we want to do is get to these coefficients, because what's missing in here, okay, we can see the random and fixed effects for our final model, but what we're not seeing is the submodels. And so to get to those, we can't actually get to them through here like we normally would. We need to run this function called coefficients, and that will pull them out, and there they are. There's the intercept and the slope for each of our models within the models. And now we can pull out the slope as our B1s and the intercept as our B0s, pull those into 2 different arrays. And the reason I'm doing this is because I want to be able to plot our data. So there's our data, and here I've color coded it by plotting each of the different groups of data, and there it is. And just so you know, normally when you do a plot, the area of the plot is going to be based around your first data set. So I first did this was just done around the red ones, and you can apply an X and Y limit to set the bounds of where the chart's going to be. Okay, so now I can take my B zeros or my intercepts and my slopes, and I can specify those, and I can go ahead and add a line for the slope through our A here. Now for some reason it's clipping off, and I had some struggles getting this to work correctly, so I'm going to go ahead and print the rest of it and make sure it works. Yay! Okay, so something up with A. I'm just going to plot it again. Yeah, interesting. Make that -10, see what happens. Nope, I don't know why A isn't coming back here. Weird. Okay, so anyway, now you can see here's our groups, and here's our models within the models. So the first level models are these ones, and then the second level is the model that created those coefficients for the first level model. And so that's the idea of this hierarchical level model. Thanks.